In this video, we'll be looking at UnionFind data structure. First, we need to define what is a partition of a set. A partition of a set M is a collection M1 to Mk of subset of M with the properties the subsets are disjoint on cover M. That is, M intersect Mg is equal to 0 to the empty set for all I different to j. And M is equal to the union of all the subset M1 to Mk. Set partition naturally arise in graph problems such as connected component. Each vertex is an exactly one component of a graph, connected component of a graph. The subset Mi are sometimes called the blocks of the partition. When we look at this data structure, there is two operations that are important. We want to maintain a partition M1 to Mk of the set M and support two operations. The union, which is joining two subsets into one, and find, testing whether two elements are in the same subset. Note that after the union of two subsets, the resulting UnionFind data structure is still a subset or a partition of M. To simplify the notation, we construct a bijection between the element of a set M and the integer in the range 0 to n excluded, where the size of M, or the number of elements of M, is equal to n. In that case, I can represent the set M as the set containing the element M0, M1 to M minus 1. So here, instead of using M0, M1, and so on, in the rest of the video, I will use the number 0, 1, 2, and so on, just to make a mapping between the two. Or in fact, what I can do is to store all these elements into an array of size n, the number of elements. So at the start, I'm going to start with all the elements in a separate subset. So in fact, I'm going to have, for a set of 7 elements, 7 different partitions. And here they've got all a different color. So I've got the partition containing only the element A, a partition containing only the element B, and so on. To represent that they are a single partition, what I'm going to say is all of them are referencing each other. So in the index, in my array, I'm going to put at index 0 the value 0, meaning that it is the root of my set or my tree. For B, saying that it's a root of itself, I'm going to have the value 1. For C, I will have the value 2, and so on, which is the same value as their index. Now I want to do several operations. I want to do some union between different subsets. And I will have to use the find as well time to time. So first, I want to union the subset A with the subset B. Both of them contain only one element. I need to pick one as the root of my subset. So here, I'm going to define that B is part of the subset of A. In that case, I'm going to say that A is the root and B is the child of A. It's in a way representing that subset as a tree. And I'm going to signal here in my array that A is the root. And therefore, B is going to point to its parent. In that case, the root A. Then I want to do union of F and J. So here, I'm going to make the union between the two elements. I'm going to say that J is going to be the child of F. And therefore, I'm going to change the value in the array at index 6 to 5. And F, it will become the root of that subset, because I'm representing the subset as a tree. I want to do a union between E and G. And here, that's where I need to be more careful. First, I need to find what is the root of J and what is the root of E. So here, it's not difficult to find the root of E, because if the element in the array for the position E is equal to the same index, then that means it is the root. So here, the root of E, the root of that component is 4, E itself. But when I look at J, here, the value is 5, which is not the same as the index of J. Therefore, J is not the root of the component. So I need to find where that root is. So I'm going to move to element 5. Element 5, it's got the same index and same value, meaning that F is the root of that component. So here I can say that the root of the component Fj is F, and the root of the component E is E. And now that I've found the root of these two components, I would say that the root of the component E will become F. So you can see that the component in light yellow contains 3 elements, and it is represented as a tree with F as a root. So now I want to do union between C and D. So it's going to be very similar to what I've done. And here I decide that C will be the root of that component. Now I want to create another union, and here is going to be between the D and J. So again, I need for these two components to find the different root. So let's start with J. Here J has a root F. Now I'm going to look at the component D and see what is the root of that component. It's 2. So here I can see that the component of D has a root C and the component of J has a root F, which are 2 different roots, meaning that these 2 subsets are disjoint. And I'm going to say that F is going to become the root of these 2 unions as a result of the union. Something to see here. Be careful, you can see that D hasn't changed. So D has for parent C, not the root itself. But I can find what is the root of the component D by following from D to C and then from C to J to F, using the index in my array. Now I want to do the union between B and D. So again, I need to find the index, the root of both components. So for A, it's pretty straightforward. I'm looking at the root for the component B, which is perhaps at position 0. I go to position 0, and I can see that at position 0, I've got the value 0, and therefore I'm at the root, and the root is A. When I'm going to look at J now, at D now, I need to look at D. D is going to point to C, which is going to point to F. So I follow the index here. So from D, I need to go to index 2, which is C. The value stored at index 2 is 5, which is not the same as the index. So I need to follow that path. So I'm going to move to index 5. The value stored at index 5 is 5, the same as the index, and therefore I'm at the root. And here, the root is F. So I can see here that these 2 elements have the same, have different root, and therefore I can make a union of the 2. Again, you can see that the index of B has not been changed. So to find what is the root of B, I will have to go to index 0, and then from 0 I need to go to index 5, and here at 5 I can find the root. So it's a pretty efficient way to find, to combine components together. So the aim of this week's seminar will be to implement the pseudocode for the UnionFind data structure. Let's look at another case here. Let's look at these 2 sets, and I want to make the union between B and U. So first I need to find if they are part of the same component or not. So let's start with B. You need to look at A and then F. You need to look at V, then T, then X to find the root of these 2 components. And you can see if they get larger, it's going to become less and less efficient. In the worst case, I may have even got n degree in the tree, a depth of n degree. So that's going to take a lot of time to do that, finding the root. The merging between the two is going to be constant time, but finding this, if they are part of the same component, will be costly. So there is a performance issue here, but I can improve that using path compression. So let's look at finding u in my component over here. And when I'm going to do that, I'm going to modify at the same time my tree. How do I do that? So I'm going to look at the method find u. So I'm going to go to index 2, the index of u. And here it tells me to follow to index 3. Then I need to go from index 3 to index 1. Then from index 1, I need to go to index 4. And now I'm at the root. And here, if I'm using a recursive function, I will be able to track back my recursive stack. And I may be able to change the value. So when I find that root, I know that the root for this component is 4. And when I'm going to go back via the recursion call, what I will do is update all the elements that I've been through, which don't have that root as values. So I'm going to go back to my previous call. So I'm going to look at this one. The value is 4, so I've got the right value for the root for that element. So that's fine. Then I'm going to go back to this one. And here I can see that the value wasn't the same. So I can modify it when I finish my recursive call for that call in particular. Then here I need to go to the previous call. And then the value was 3, so I need to change it to 4. And by doing that, look at what's happening to my tree. My tree is going to be changed into this 3. And you can see that the long path I had between u and x has been compressed to only one edge. And therefore, to find if u at the next time is part, to find the root of u will be just one step. Some of them, like s, because I didn't look into them yet, have already still an old value. But when I'm going to do a find s, I will be able to correct the path and to compress the path for s. That will make the find and union much more performant. In fact, it will be constant time. Because the biggest depth I can get will be 3 at any time. So that's a very, very performant algorithm and a very, very useful data structure. So the aim of the scimitar will be to implement UnionFind with the path compression. And to do so, I will need to use recursion. In the next video, we're going to look at another algorithm to compute the minimum spanning tree, looking at cruise call algorithm.